we want to show that this function has exactly one zero or one x-intercept in the interval from -1 to +1. Okay? So in order to answer this question, in order to be able to prove that there's exactly 1, 0, first of all, we're going to really focus on those endpoints. Let's find g of -1, and then let's find g of 1. Okay? So g of -1 would be 1 over 1 minus -1, so 1/2, plus the square root of 1 plus -1 was 0, minus 3.1. So 1/2 minus 3.1 will get you a value there. So g of -1 is going to be -2.6. Okay, let's do the same thing with the other endpoint. So g of +1. So 1 over 1 minus 1 is 0, not going to happen on that point, plus the square root of 2 minus 3.1. So g of 1, it would have been -1.7, but because of this whole fact right there, we have an undefined portion, then technically g of 1 is undefined. Okay, so how are we going to answer the question? Normally, if you had one endpoint giving you a negative value and one endpoint giving you a positive value, then you would say, okay, obviously you had to cross the x-axis somewhere in there. So how are we going to figure out this otherwise? Well, if we really kind of analyze a little more closely of just the domain of the graph, if you look at the first term in the function g of t, what this bottom is telling me is that we know for a fact that t cannot equal 1. Okay? And if we look over here at the square root portion, remember I can only take square roots of positive numbers, and so that's telling me that t always has to be greater than or equal to -1. So combining these together, in a sense, it's almost like we're getting a domain of basically saying we can go from -1 up to 1, can't include 1 though, and then we can go from 1 to infinity. Okay? But specifically, we just want to look specifically from -1 to 1. So really right in here. Well, we know at -1 we got a negative value. It's at -2.6. So since we can't really include +1, let's get something really, really small to it and see if it comes out positive. So how about g of, I don't know, let's do 0.9. That's really, really close to 1. If it comes out positive, then obviously we're going to see that we crossed from the negative portion of the x-axis to the positive portion, or from below the x-axis to above the x-axis, and then we can show then for sure that we have one x-intercept in there. So g of 0.9. I would just honestly get out your calculators, because there's going to be crazy to do this in our heads. Maybe. I don't know. I know I can't really do much of a square root, but so 1 plus 0.9 would be 1.9 minus 3.1. So I'm going to cheat and I'm going to pull out my calculator. And when I do that, I get a value of 8.28. So look at that. We're going when I'm getting really, really close to the other endpoint value, we're going way up there in the positive. So if I go from a negative side to a positive side, then it's showing then for sure I have exactly 1, 0 in there. And then one last thing that we can possibly do, start erasing this while I talk real quick, is we can check all about the derivative. Okay? So if we can take the derivative of the function and it comes out kind of positive, or in the sense that we know that it will always equal positive, that's really going to help, because that's what it's telling us is the graph is always increasing. So it's just going from the negative value on the left to the positive value on the right. We know it has to be always increasing. So let's see if we can see anything into the derivative here. So of the function, let's do the bottom, 1 minus t times the derivative of the top, minus the top times the derivative of the bottom, over the bottom squared. Okay, and then plus the derivative of that would be 1/2 times 1 plus t to the -1/2, and the derivative of -3.1, of course, is 0. So cleaning this up, that goes away. We get 1 over 1 minus t squared plus, let's write it like this, 1 over 2 square roots of 1 plus t. Okay, so let me show you something here, and this is the way we can actually even confirm it even more than ever before. You know, no matter what I plug in here for a value of t, I mean obviously other than 1, but at least in our interval, that no matter what I'm going to be squaring it. So anytime I square anything positive or negative, it always comes out positive. So no matter what's coming from this side, it's going to be positive as long as I stay in my interval. And then over here, again, as long as I'm in my interval, remember what comes out of a square root sign is always positive. So if I take a positive number and I add on a positive number, this is telling you that your slope is positive. So between -1 and 1, the graph is increasing. And since at -1 it starts below at -2.6, and at 1 or close to 1 we get an 8.28, therefore it has to only cross once. Alright, now that we've beaten that to a bush, let's go on to the next example. We want to show that this function has exactly 1, 0 in the same over the interval from -infinity to +infinity. So kind of going back to my graph just to double check, or the function, just to double check to make sure I agree with this. Yes, with cosine, that no matter what that angle is right there, it can be anything. You can take the cosine of -1,220 degrees if you wanted to. And then same thing with the positive form. Okay, so let's go from here. Let's start the problem. And this time I'm going to start with the derivative portion. So let's look at r prime of 0. So the derivative of 2 theta is 2. And the derivative of cosine squared will be pull down the 2, cosine theta, and then times the derivative of cosine theta, which is negative sine theta. And then square root of 2, of course, is 0. So the derivative, r prime, is going to equal to 2 plus 2 cosine theta sine theta. Okay, so when we analyze this derivative right here, what it's basically saying, no matter what, I'm going to have the number 2, and then on top of that, I'm going to add on some value. Okay, well, think of cosine and sine. The maximum values they ever get to is either 1 or -1. Okay, and when you are at those extremes, when you're at way out there at +1, then one of them's 0, and that would knock it away, and you just get 2 plus 0. Okay, so if we think we have to come in a little bit closer to that, let's say even at most that by the time I picked a value, let's say cosine of 1 degree, just think about cosine of 1 degree, then it could be potentially 0.9, and then your y value there would be 0.1, but it's still positive. Or if you went over in quadrant 2, back there, let's say 179 degrees, okay? So you have a really large x value really close to, let's say, -1, so it'd be like a -0.9. Y value would be positive, so 0.1. All of that still times 2. By the time you add on 2, this, no matter what, it's going to be something smaller than 2. So that by the time you add on 2, your derivative is always going to be positive. So r prime is always positive. And if you, nothing else, if you want to double check with me, why don't you get out your calculators and just start plugging in angle values. Like I said, look at 179 degrees where you know the x value is negative and the y value is positive. And you really only have to check quadrants 2 and 4, because in quadrants 1 and 3, no matter what's coming out over here on the right, it's going to be positive. It's going to be larger. You're going to start with positive and even add on any more. Okay, so now we always know that the graph's going to be increasing. Let's say so r of theta is always increasing. So that's a good sign over the whole entire interval. So over -infinity to +infinity, that's what we just found. No matter what, it's always going to be increasing. Now we just got to show that, obviously, since it's increasing, you've got to, and that there's no like undefined, no points of undefined, then really technically we can say we're done, because a graph can't just start, let me draw a picture, your graph can't just start here and go off to here, because our domain is all real numbers. And our derivative just showed us that it's going to be, no matter what, you know, always increasing. So that means I have to cover all of the graph from negative to positive, and it's going to cover all real numbers, and it's always going to be increasing. So that's just technically, by just knowing this and knowing that our derivative is always positive, we've answered the question. Okay, so example 5. We want to find all the possible functions with the given derivative. Okay, so what this problem is really asking us to do is almost go a little bit backwards. We need to identify y, knowing that this is y prime. So we need to kind of work backwards just a little bit. So what I'm going to do to answer this is I'm going to write where I can see really the exponents. So this is saying 1/2 x to the negative 1/2. So what did the function have to be that by the time we went through the derivative rules, we actually got this? Well, y is equal to x to the 1/2, right? Because if I started here, I moved that exponent down front, and then I subtracted it, or subtracted 1 from 1/2, I would get right back up into there. The only difference here is we're going to do this thing, we're going to add on this constant. We're going to say plus c, because technically, where c is going to be any number like positive, negative, decimals, fractions, but it can't have a variable with it. Because remember, if I started right here and I asked you to find the derivative of any constant is always 0. Okay, but we want to include that in there because that's why it says find all possible functions. Well, that c is going to represent all the other possible, all the potentials. It's no matter what, it's got to have x to the 1/2. It's just, it could be x to the 1/2 plus 1 or x to the 1/2 minus 10. It's just, and throughout the derivative steps, that minus 10, that plus 1 is always going to go to 0. Okay, so here's the answer for part A. Let's go to part B. Okay, looking closely into this one, it's basically saying x to the negative 1/2. So what did the original function have to look like so that by the time that we took the derivative, this is what was left over? Okay, so let me just play around just for some thoughts real quick. I needed to have a number out front. Let's say, oh, I don't know, maybe like, let's say if we had 2. Let's try this. Okay, so normally if I started here, if I brought down the 1/2 to the front, so 2 times 1/2 would give me the 1, and then by the time I subtracted 1 from here, then I would have gotten it. There you go. And then of course add the plus c for all the other different varieties of adding on a constant value. Okay. Let's go to this next one. So y prime is 4x minus x to the negative 1/2. So this part we can kind of already do. We just did that on part B. So y is going to equal, okay, what do I have to have? Obviously an x, I would say 4 here. So by the time I chunked it down there, I got the 4. But if I normally took the derivative right there, I would have a cube right there, wouldn't I? So what are we going to do to fix this one? Well, let's think a little bit. What if instead of having a power of 4 up there, what if I had just another different number in front? So like, let's say, what if I had 2 right there? So what exponent times 2 would give me 4? Well, how about that? So that way by the time I drop the 2 down front, it would be 2 times 2 is 4, and then that would leave me behind with an exponent of 1. And then of course minus 2x to the 1/2 for the next part, and then plus c. Okay, so that would represent all those different functions that would have y prime equals 4x minus 1 over the square root of x as a derivative.